Welcome back. This will be our last installment of our lesson involving the chain rule for derivatives. Now we needed to learn the chain rule technique for other basic functions, and that allowed us today to look at another function we don't know the derivative of yet, and that was the natural log function. And this will be one you should fill in on your derivatives sheet when we're finished. So I could I've left the boxes blanks because I'm going to repose the question and try and work it out for you how we know what the derivative of the natural logarithm function is. I could repose the question as y equals, or f of x equals, let's do it like that actually, f of x equals the natural logarithm of x, and we want to know what is f prime of x. Okay, now what's going to be used here is we want to rewrite this equation in a different form, in a form where I would actually know how to apply a derivative. And so what I'm going to do here is rewrite this by solving for x. Okay, if the natural log of x equals f of x, it's equivalent to writing e to the power of f of x equals x. If that is confusing, just think of a different situation where you would do that exact thing. This is just like this. In algebra class, if you knew that the natural log of x equaled 2, you should also know that x is equal to e to the 2. Okay, so all we're doing here is treating the symbol f of x as if it were the 2, and then e to the power of both sides yields this equation right here. Okay, so now anytime I have an equation, if I apply a derivative to both sides, that's going to produce another equation that I can say is true. This is no different than when you multiply an equation by 2 on both sides or subtract 5 from both sides. Applying a derivative to both sides also produces an equation that's true based on the previous one. But this time I know how to apply the derivative to both of these. The derivative of the right side is the derivative of x with respect to x, which is 1. On this side, we're using the chain rule. Okay, it's like u equals f of x. And now I'm really finding the derivative of e to the u, which is e to the u times the derivative of u, right? So this is going to be e to the f of x times the derivative of f of x. Okay, so we use the chain rule on that side. Now remember, our question at the beginning was, what is the derivative of f? So I have that right there, but I want to solve the equation for f prime now. I'm going to divide both sides by this other factor. So to solve for f prime, I'm going to divide by e to the f of x. So I have an expression for what I was going for, but I don't want to leave it this way. I remember back at the beginning that f of x was the logarithm function, right? And that meant that this is 1 over e to the ln x, and that identity is x. So my derivative at the end, f prime of x is 1 over x. That's the punchline, and that's what we're going to write up here. So the derivative of the natural log of x is 1 over x. Now, most of the time, it will not be just log x. It might be the log of x squared or the log of 5x, in which case you make a u substitution and use the chain rule. So the chain rule version of this would be that the derivative of the natural log of u is 1 over u times the derivative of u. That will account for other situations like the derivative of the log of 5x. Now, what I also find a good way to write this is to write this as 1 over u times u prime over 1, and then just put the two fractions together. So the numerators make 1 times u prime, and u times 1 is u. So a good way that many students just remember this rule is that the derivative of a log is expressed as the derivative of what's inside the log divided by what was inside the log. So we're going to have a couple examples of this. And we'll also show how using some prior knowledge like logarithm properties will help you find derivatives of logarithms a nice way also. Okay, and we're actually going to review that before we start. At the top of my slide here, let's review some logarithm properties that you learned in algebra class and probably relearned last year in pre-calc. They go like this. What is another way to write a log if it's two numbers are being multiplied and then you take the log of that? You learned that that's the same as taking the log of the first number and adding it to the log of the second number. So I'm going to write this rule like this. This is not calculus. This is something you learned in pre-calculus. If two numbers are multiplied, then you take the log of that. You can also do this by adding the logs of the two numbers. There's another property about quotients. You divide two logs, or the divide and then take the log. It's like taking the log of the numerator and subtracting the log of the denominator. And there's a third one. If you take a number and raise it to another power, and then take the logarithm of that, you can multiply the power times the log of the base. Okay? I want to make sure you keep your eye on these and look for ways to use them as a way to make the derivatives of logarithms go easier. You don't always have to use them, but they can come in handy. So we want to make sure we look at a couple examples of that. The three functions I want the derivative of first all involve the natural log function, but in different ways. Notice the first one, the logarithm of x is here, but it's being multiplied by x. That should just get your attention right away that this is a product, and therefore we need to know the product rule. Also, where the first factor is just x, and the second factor is the natural log of x. So when I go to work out my derivative, I should start by making the template for the product rule. And now I'm just going to say my rule, 1 d2 plus 2 d1. So the 1 is x, and the d2 is the derivative of the natural log of x that we just learned. The derivative of the natural log x is 1 over x. And then over here I'm going to do 2 d1. So 2 is the natural log of x. d1 is the derivative of x, which is 1. And then let's look for anything obvious to simplify. I would say the only thing really is this, because x times 1 over x should just be x over x, which is 1. And then anything times 1, we don't have to write the times 1. So this is 1 plus the natural log of x, and I would call that my answer. Now, number 2, one way, I'm actually going to demonstrate two different ways here. One way would be just to treat this as the natural log of u, and we're going to let u be x squared. And then my main function is y equals the natural log of u. And so now my derivative is going to be the chain rule for the logarithm function, u prime over u, which means the derivative of x squared over x squared. But then the thing to simplify here is I can divide out x. So my simplest answer would just be 2 over x. Okay, and that seemed all fine and good. Now, here's an alternate thing to think about. Remember the logarithm properties, especially the third one. It says the logarithm of a power can be rewritten where you bring the power down and multiply it by the log of the base. So I'm going to attempt this one again by rewriting the problem y equals 2 times the natural log of x. And this time I'm not going to need the chain rule for my derivative, because now all I have is a constant multiple, 2 times the log of x, and I'll need to multiply by the derivative of the natural log of x, which is 1 over x. And you notice I'm going to get my other answer just as well, 2 over x, because 2 multiplies by 1. And so my derivative is 2 over x again. Notice this time I did not need the chain rule. Okay, so there's a bit of an advantage on this one to just using the logarithm property first. Okay, so here's my third one. Let's try it the same way I did this one up here, and that is let's just let u be the entire quantity x cubed plus 2x squared. And so again, my main function is y equals the natural log of u. So my derivative rule is derivative of u over u, and this time I can fill both those in pretty quickly. In fact, the derivative of u is the derivative of x cubed plus 2x squared, so 3x squared plus 4x, and then u was x cubed plus 2x squared. And now that's finished, other than I noticed that every single term has at least one power of x. So why don't I just factor out x from every term and reduce the fraction down one more time. So I would say now my derivative in simplest form is 3x plus 4 over x squared plus 2x. And there we have it. I'll finish this set of examples with a derivative you want to calculate where you really want to make use of those logarithm properties. I see a quotient or fraction inside of this logarithm. So this reminds me of this logarithm property right here. The logarithm of a quotient, a over b, is written also the log of a, the numerator, minus the log of b, the denominator. I can really make good use of this to make the derivative of my logarithm function be much simpler to find. I'm going to rewrite my problem, y equals the natural log of x plus 2 minus the natural log of x minus 1. So even though I've got two separate parts now, the derivative of each part is way simpler than trying to work it out from the beginning and leaving it in the form it was in. Because watch this. Now, you look at this first log, what you want to say for yourself here is u is x plus 2. So this is the natural log of u, and your derivative is u prime over u, where this u, and this one u is x plus 2. And then on the second one, you can do that again. Maybe this time u is x minus 1. And the derivative of the log of u is once again u prime over u. Now you just have to keep track for yourself that on the first one, u is x plus 2, and on the second one, u is x minus 1. But now, this is pretty easy to write down. In the first one, the derivative of u is the derivative of x plus 2, which is 1, and u was x plus 2. And in the second one, it's very similar. U prime is the derivative of x minus 1, which is 1, and u is x minus 1. And at that point, it's over. Derivative is 1 over x plus 2 minus 1 over x minus 1. So if you wanted the slope of this function at a point, you would at worst plug in a number for the x and then subtract two fractions. That wouldn't be too bad. Now, just for a minute, if you have a minute, let's point out the alternative to what I did here. This was actually not too bad if I expanded the log using this logarithm property. If I don't do that, watch what's going to happen. Maybe you just start with this and let u equal the fraction x plus 2 over x minus 1. And so your main thing to differentiate is the natural log of u. And so your derivative is u prime over u. Now that wasn't too bad, but the resulting expression is very messy. Because watch this. U was this entire fraction. Okay, so we've got to divide by that whole thing under here. So right away we've already got a fraction within a fraction. But we're not done. Now we have to work out u prime. Well, look at this. U is x plus 2 over x minus 1. So for u prime, guess what? We need the quotient rule for u prime. So we have to do all of this other work here. We have to do low d high minus high d low all over the square of what's below. Fill it all in. Low d high would be x minus 1 times 1. High d low is x plus 2 over times 1. And then the square of what's below is x minus 1 squared. Now look at this here. We would have to take all of this and put it in there where u prime is. But maybe we'd simplify it first. This all just makes x minus 1. This all just makes x plus 2. Now just be careful. Look, there's plenty of opportunity to make an algebra mistake here. I've got x here minus x, so that's 0. X minus x is 0. But then I've got minus 1 minus 2, and that's minus 3. So my derivative, u prime, is negative 3 over x minus 1 squared. Even then, this is not very simplified, okay? You could do some more algebra and try and get this all down to a single fraction, right? But in my opinion, why would we want to do any of that when the first way was so much better? If we expand the logarithm first, the derivatives were very easy to calculate. Okay, look at all the opportunity for algebra mistakes on this side. So even though this is correct also, it's much harder to work with. I think this is the better solution over here. Okay, they're both correct, but I think the one on the left is easier to work with. Well, I hope this helps you guys with some more problems on your assignment sheet. Please don't hesitate to email or get a hold of me if you have any questions on any of the homework in section 4. Okay, and next time we're in class, we'll be starting section 5, implicit differentiation. Have a good day. We'll talk to you soon.